Microphone is good. Thank you, Friday audience, for being here till Friday. Thank you, organizers, for having me here. So I'm going to tell you about twisted WSE2, which is sort of the Moiré thing that I've been working on most in the past couple of years. Those of you who don't know me, I'm at Columbia, also at Brookhaven. Let's go. Okay, so let me first acknowledge the people who did the work. So this work was started by my student, Augusto. Interesting story is he started this work on the basis of a rumor. Once in 2019, I was standing next to Philip in Italy, and Augusto was standing next to me. And I asked Philip, what are you doing on this Moiré stuff? Because it was just very hot then. And Philip said, oh, we are measuring twisted WSE2. And I said, did you measure anything interesting? He said, maybe a superconductor. I said, oh, what is TC? He said, maybe 1 Kelvin, maybe 10 Kelvin. So what is this, 1 Kelvin, 10 Kelvin? So Augusto was standing next to me, said, I'm going to go home and I'm going to start making these samples. Okay, so that's how, at least in my group, this started. Augusto got hold of one of Corey Dean's students, this was Enmin, and we had a joint postdoc, Lei Wang, who was a real expert on all of these things. He was part of the original BN crew. All these people are moved on to various places. Now, in sort of closing the loop, Lei's student Ling Nan, I'll show some of the data from one of her samples, has now come to Columbia to do a postdoc with me, and Xiaodong in Washington, she's delocalized. We rely on crystals which are very high quality, which come from Jim Hohn's group. I also take part in that effort a little bit. Of course, the HBN that all of us live and die by. I'll show you some stuff from theory. So this is Andy Millis, and Andy Millis, like Senthil said, polarons is a polaron. Many people keep accumulating around him over time. So there's an older group of people who have results, and then there's some more recent pictures that I'll show you, all of that. And then some DFT from our good collaborator, Angel Rubio at Hamburg, and his group. Okay, so here is a program of what I want to talk about. So these are all on the archive or published in some way. I'll first talk about some prehistoric work back from the old days of 2020. This is just to set the stage for twisted WSE2 and what the basic phenomenology in this system are. I'll spend very little time on this paper, which is one of the first theory papers from Andy's group, just talking about various instabilities that one has in twisted WSE2. And then I'll spend most of the time talking about two recent papers, which are both on the archive. One is we can see evidence now for Fermi surface reconstructions, or what we believe are antiferromagnetic states, and these are not tied to insulators in the sample, these are metallic states. And then the most recent thing is superconductivity, and I'll show you that it occurs near this Fermi surface reconstruction. So I'll try to spend most of the time on these things. Okay, so let's start with the first story, which goes back a few years. You've all heard this before in this meeting, so I'll be very quick about this. This is twisted WSE2 showing a particular cut through the band structure. It has two layers. This is homobilayer, and so it has two valence bands. All the physics I'm going to talk about is in the valence band. And initially, these two valence bands don't talk to each other. When you put them on top of each other, then they hybridize. They form an anti-bonding band and a bonding band, and that's what the band structure is. And all of the band structure that I'm going to talk about is sort of related to this part of the story. So in this early work, what we showed is that as you dope these samples and you measure transport, then when you're at half filling of this Moiré unit cell, then you have an insulator. I'll apologize to Shankar already. It's not as good an insulator as Shankar would like, but it certainly has an activation gap that you can measure. The position of this insulator is always tied to half filling, and since as you change the angle, the size of the Moiré unit cell changes, the position of this insulator in absolute density units also changes as the size of the Moiré unit cell changes, and all of this makes sense. So one of the very important knobs in this story is displacement field. You've also heard a lot about this. Displacement field or electric field applied perpendicular to the layers. If I have two valence bands that are separated spatially from each other, when I apply an electric field, the on-site potential energy is going to be different, and so there's going to be a displacement between these. So what this means is that the electronic structure is actually tuned when you apply this electric field. So seen here, this is one layer, this is the other layer, and you can see them displaced relative to each other. This is a somewhat old DFT calculation from our original paper, but I think not too inaccurate. One thing that I'll point out, which I'll come back to several times, is in this topmost valence band, you can see there's a Van Hove singularity. You can't see it very clearly in this cut, but this is a Van Hove singularity that's at the M point. And as you apply this displacement field, this Van Hove singularity moves away from the M point, and eventually it reaches the K point. I'll talk about that as well later. So if you just plot the density of states of this very topmost valence band, this is what this thing looks like as a function of electric field. I should say that this is wrong. More recent calculations, the peaks are actually different in order than what's shown here. But what I want to draw your attention to is how this Van Hove singularity progresses as you apply displacement field. So as you start with zero displacement field, in this system, the Van Hove singularity is located to the right side of half filling. And right side here means this is the valence band edge, so it's closer to the valence band edge. And as you start to apply displacement field, this Van Hove singularity goes through half filling until eventually it runs away all the way to the end of the band. Okay. So we gave our, we call this a magic continuum, which the referees did not like, which is fine. And what we showed is that the insulating phase that we see in these samples occurs for some range of twist angles between 4 and 5 degrees, is what we were able to measure at the time. And it's bounded both in density, so it occurs for some range of density, and it also occurs for some range of displacement fields. So if you're at very small displacement field, you don't see insulating behavior. If you're at very high displacement field, you don't see insulating behavior, but it occurs in some range of displacement fields. It's a displacement field axis where insulating behavior is seen. Then what we try to make the story is that this is tied to how the Van Hove singularity moves through the system as a function of displacement field. So the idea was that as the Van Hove singularity goes through half filling, that's where perhaps correlations are the strongest, and that's where you see this insulating behavior. And if you move this Van Hove singularity sufficiently far from half filling, then correlations are weaker, and you don't have this insulating phase. So that was the story there. So that's all I have to say about that. That's sort of the preliminary to what I want to talk about next. So then Andy and folks did some theory to consider what possible states, what possible orders one can expect to see that could be related to this insulator. And this is their picture, and they have this phi, which is like the displacement field. So this phi tunes where the Van Hove singularity sits in the band. And in these original papers, this was just mean field theory. And so in mean field theory, you will see various orders when you're close to this Van Hove singularity. Generally, that's where density of states is high, and you'll see various things. I'm showing you just one result. Now, I will apologize. I think many of you in the audience have worked on this and have many theories, so I apologize in advance. This is just a picture because I like it has many colors on it. And what it says is that all kinds of magnetic orders are possible, and they do some calculation within Hartree-Fock, which Sentilas told us we should look at, but not look at too carefully. One of the things that we like to believe is prominent in this is this 120-degree Néel order. That is formed in this system. But you can see that there's all kinds of other orders that are possible within this theory. So the generic picture that Andy and company told us, Andy told us that as you tune density, what one expects is that one enters one of these ordered phases depending upon where exactly the Van Hove singularity is. If the Van Hove singularity is here, you expect to start to see this ordered phase somewhere around here. And in general, at least within this theory, this would result in a metallic state with some magnetic order, antiferromagnetic or even ferromagnetic order. And then as you come to half filling, if the order is sort of strong enough to completely gap the Fermi surface, you have some insulating phase that's formed. This magnetic phase might persist even beyond half filling until at some point it disappears and it becomes a regular normal metal, paramagnetic metal. Okay? So this was the picture from theory. And now what I want to tell you about is some evidence for the idea that even when you're away from this insulating phase, that you still have some magnetic order or some order in the system. Okay, so that is this work that's on the archive and under review. And what I want to show you here, so here I'm showing you, this is the Hall effect. So this is the Hall resistance. This is taken at a fairly small magnetic field. So this is 1 Tesla. And this is as a function of density on this axis and displacement field on this axis. And for technical reasons, we can only measure within this region. And what I want to tell you, I won't show you proof here, but just take it from me that the insulating behavior, that is the region where the sample becomes more resistive as you go to low temperature, is confined to this region within this phase diagram. And everywhere outside here, the sample is a metal, at least as far as resistance goes. As you lower the temperature, the resistance gets smaller. And again, this is sort of a picture of what the density of states should do as a function of displacement field. And now what I want to show you is I want to show you here 3 sets of data. These are data taken as a function of density. And these are acquired at 3 different values of displacement field, so 3 different positions of the Van Hove singularity. And what you'll see is something quite interesting. So let's start on this side. So on this side, this is where the Van Hove singularity is somewhere close to half filling. What you see here is you see this dark red region. This is RXX. This is a resistive region. This is our region of insulator at half filling. And now go all the way over to this side. This is at a different value of the displacement field. At this value of the displacement field, the Van Hove singularity has moved to exactly that position. This is nu equals 1.2. I'm sorry, 1.2 should actually be 0.6, so it is 0.6. Sometimes we write it as 1.2, sometimes as 0.6. Half filling is -1 in this notation. So the Van Hove singularity is beyond half filling. I hope all of you can see in this particular plot that there is no hint of any insulating behavior at half filling, or indeed anywhere in this plot. There's no insulating behavior. One nice way to see that this is the Van Hove singularity is what happens as you apply magnetic field. So as you apply magnetic field, in general, you have the spin up and spin down values. And if everything is non-interacting, the spin up and spin down values should split from each other because of a Zeeman splitting. And so the one Van Hove singularity at 0 field should result in 2 Van Hove singularities at high field. And I hope all of you can see these lines. There's 2 nice lines here. This is precisely the Zeeman splitting. There's 1 Van Hove singularity there. There's another Van Hove singularity there. And you can see the same thing here. You can see the same thing here. It gets a little more confusing in this particular region. Okay. Now, what then I want to talk about, what comes after, is what happens as you go from here. This is what I would call Van Hove very far from half filling, very weakly correlated region, to this region where the Van Hove is not quite at half filling. The Van Hove is somewhere close to half filling. So there's still no insulating behavior at half filling. But I hope you all see that there's some funky stuff going on there. And I want to talk about that funky stuff. I want to also show you another, just as an aside, something interesting. You can see how correlations affect the system. If you see, for example, the Zeeman splitting. So the Zeeman splitting, you can get a sense of from how far apart these 2 Van Hoves are at a given magnetic field. I draw 2 lines here to show you how far apart they are at this value of displacement field. If I take these 2 same lines and I translate them to here, you can see that the G factor has increased quite enormously when I go into this more correlated regime. Just one example of how it plays. Okay, so now let's go to this region where I'm not quite at the insulating state and I'm not in the extreme weakly correlated state. And I'm also showing you here the Hall effect, which with this color plot looks very confusing, but I'll try to demystify this Hall effect. And all of my analysis is really based on an analysis of the Hall effect in this region. Okay, so let's talk about the Hall effect, and let's talk about the Hall effect in this region. And let's start with the expectation from a non-interacting semiconductor which has only 1 band, and you're going from one end of the band to the other end of the band. You're starting from a valence band, so you're starting with holes, and then at some point when you reach the end of the band, you have to end up in an electron pocket, and between the 2, there's a Van Hove singularity. And I'm a simple guy, so this is the formula I've been taught for the Hall effect. And if you take this formula and you plot this formula for non-interacting electrons, I start with the Hall effect for a small number of holes, so large Hall resistance. It keeps going It hits this Van Hove singularity where the hole Fermi surface turns in an electron Fermi surface. So there's a switch in the sign of the Hall effect. and then it keeps going on its merry way till it reaches the end of the band. And now let's ask ourselves, can we measure this Hall effect? And I'm going to do this at a reasonably small magnetic field, half a Tesla or 1 Tesla, where we can still be sort of in the linear response regime. And I'm going to show you traces of the rho xy as a function of magnetic field at different points. So if I sit far from this Van Hove singularity and I measure rho xy as a function of B, it follows my formula, it's linear with B, I can extract a slope, I can compare it to the density that I expect on this plot, and within reasonable error bounds, it matches what I expect. I come a little closer, the slope of this line changes, but essentially it stays the same. And now let me come even closer to this point, and now I see something quite funky. I see that rho xy no longer looks like a line, it looks like a line at small field, but then you see this change in the slope of rho xy, and this is very typically what you would see if you have multiple pockets in the system. So if you have 2 pockets in the system, this sort of Hall effect is expected. And then now I'm going to cross this Van Hove singularity, and I'm going to go sufficiently far on the other side, and then I see indeed electrons in the Hall effect. And again, I can calculate the slope and compare it to what I expect, and if I'm sufficiently far from the Van Hove, again, it matches my expectations. All right, so this is what I would have expected purely on non-interacting electrons with my standard formula, and this is what we see instead. And so this is our evidence, our primary evidence, that something funky is going on in this region of the Van Hove singularity, and in particular, that we have some sort of Fermi surface reconstruction that gives me both electron and hole pockets at the same time, which gives me this nonlinear Hall effect. And here I'm just plotting all of the Hall data in this region, and you can see it go from one sign to the other sign, and in between go through this funky stuff. Okay, now you can ask the question, is this really some sort of phase in the sense that does it have a well-defined phase transition? And so we can apply parameters like magnetic field, or we can apply temperature and ask how these things evolve. Let's first look at the temperature dependence. It's a little nicer. So you can see here was this big hump in the Hall coefficient, and as I start to heat up the sample, and this is going up to 30 Kelvin, you see that now it looks much more like what I expect for the non-interacting Hall effect. It just kind of smoothly goes over from one side to the other, okay? And this is the same data, but it's plotted now as a function of temperature. So what you can see is that if I look at rho xy, which is the lower set of these curves, rho xy, as soon as I go above about 20 Kelvin, all of the curves collapse onto each other, so there's no temperature dependence, again, as I would expect for a single band system. Rho xx still has some temperature dependence, that's fine. And so this is some evidence, perhaps, that there's really a phase, and this phase has some phase transition, which is on the order of 20, 30 Kelvin. You know, we can't tell you very precisely what the temperature is.
Something is happening in rho xx at low temperatures, right?
Yes.
The cards are crossing each other and so on.
Yeah.
And is that something significant? Are you going to talk about that? Or?
No, I'm not going to talk about that. This is related to where it goes from, you know, t squared behavior, there's a t linear behavior, all that stuff. Yeah. Okay. Okay, so they're everywhere here. These are all metals, right? So look at rho xx as a function of temperature. All of them are decreasing. It's just the way they decrease at low temperature changes when you come. Sorry? Okay. Yeah. You can also apply a modest magnetic field. So this is going from half a Tesla to 5 Tesla. And you can see that by the time I go to 5 Tesla, I've completely killed this effect. Right? So this is perhaps some evidence that this phenomenon is magnetic. You apply some modest magnetic field and you kill this state. Of course, the magnetic field, because the G factor is strong, also affects the band structure. Right? So it's not a great evidence, but it's some evidence that magnetism is playing some role here. That by the time you apply 5 Tesla, you've now killed this peak in the Hall coefficient, and instead you have these 2 steps, and these 2 steps are the 2 separated Van Hove singularities from the 2 different spin channels. Okay, now here is now Andy's picture. So this is Andy's picture for how this reconstruction could happen, and this is a particular type of order. This is 120-degree Néel order. So here is the band structure in the absence of this reconstruction. And when you have this reconstruction, then indeed you'll have a more complicated band structure. So the Fermi surface goes from something like this to something like this, and you have multiple pockets that are present. And then you can take their expectation for the Hall effect based upon the very simple formula, but just adding together the contributions from various bands. That's highly illegal, but let's do it anyway. And you'll find a reasonable match with the experiment if you do things in this fashion. So you just count together electrons from different bands and add them together in some reasonable way. You can match the Hall coefficient that we see. Yeah, and here's a sort of more video version of this. So here what you're doing is you're sort of tuning the chemical potential. And as you tune the chemical potential to a place where this order can happen, so here it's not ordered, there's the order, the reconstruction, and then you keep tuning the chemical potential, and then that reconstruction goes away, etc.
Can I ask you a question?
Yeah.
So this is just a band structure calculation that you're showing in your video, right?
Yeah.
So, I mean, I don't like talking about RS, but this is a pretty strongly interacting system. So presumably the bands are very strongly denormalized by electron-electron interaction. So this picture you think applies even quantitatively or qualitatively?
So I think what we can say at this particular value of displacement field, we don't, for example, see any insulating state at half filling and so on. So compared to that region where you see those phenomena, it's less interacting experimentally.
You have some indirect evidence that is weakly interacting because you're not seeing an insulator.
Yeah, yeah. Okay. How am I doing on time?
You have 10 minutes.
Oh.
9 minutes.
Okay. I'm going to jump over this part very, very quickly. I want to show this to you because this was entertaining to us. Very quickly. So as you apply small magnetic field, I already told you that this insulator is killed. Let me jump over this extremely quickly. No, I should show you this picture. Okay. So this is a more recent picture of the Fermi surface at one of these displacement fields, somewhat random displacement field. Here the Van Hove singularity has moved from the M point and it's moving towards the K point and it's sitting there. And there's the two different spin channels that are here. And what I'm showing you here is the susceptibilities that are calculated from this for across the two spins and also within a single Fermi surface. So this would be like if I had a charge order, and this would be if I have some sort of spin order. So the essential point here is it looks like there's always in this kind of susceptibility to form spin order, there's always some peak that is near the K point, and this is similar to that 120-degree Néel order. And in the charge susceptibility, the only peak that's ever seen is at Q equals 0. These are other sort of weak features that are seen. Okay, and Daniela yesterday showed me better pictures, so talk to him. He has nicer pictures than this. And he didn't show me the good pictures. Okay, so the thing that I now want to be very brief and go away from is that as you apply a magnetic field and you increase the magnetic field, the system becomes an insulator again, which is quite interesting. And I'll talk to you more in detail because I want to spend time on the superconductivity. But what we believe is going on in this particular system is that since the G factor is much, much larger than graphene, when you apply a modest magnetic field, you can start to split the bands significantly, and you can reach a situation where one of the bands has a small number of electrons left in it, and the other band has a small number of holes left in it. And that's kind of the ideal situation at half filling to form an exciton insulator, because at half filling, you're guaranteed that the number of electrons here is equal to the number of holes there. And simply by applying more magnetic field, you can tune the density of these electrons and holes. And of course, it's always possible that if you apply sufficiently large magnetic field that you completely polarize the bands. And I won't show you our evidence. It's in the paper. You can read about it. I can see quite clearly that we never reached this situation. I won't show you the evidence for that. But just to say that we can reach this sort of exciton insulator phase. And let me just show you this picture. So exciton insulators, you know, there's this version in titanium diselenide, nice work from Peter Abamonte and so on. There's a lot of beautiful work from Corey and Philip and Jim and other people here, where you have fully separated systems, and you have Coulomb interaction between two layers, giving rise to excitonic insulators. This is sort of a different, interesting exciton insulator, where it is within the HOMO bilayer, but I have a small density of electrons and holes at the same time, and it can form an insulating phase. Okay, so I can tell you more about this. I want to spend my remaining time on the superconductor. Okay, so the story behind this sample is that in our 2020 paper, we had seen a sample that was superconducting. I firmly believe it was superconducting. It had zero resistance, but the sample died before we could do some of the other checks on superconductivity. Matt was not there at the time, I don't think. Okay. And the referee quite rightly said, come on, we can't let this go, and you cannot claim that it's a superconductor. So we said, fine, no superconductor. But we still stuck it in there as figure 5. So if you look in figure 5, we say possible superconductor. So Yinji, who's Corey's younger student, after Augusto left, she was asking what she should do, and she said, let's make that 5-degree sample again, and let's see if we can reproduce this superconductivity or something else. And Yinji measured this sample at, I think it was 1 Kelvin, and she saw nothing. There was, in that original 5-degree sample, there was an insulator. Yinji didn't even see an insulator. And so Yinji was very disappointed. She came, she talked to us. The data were very beautiful, but there was no insulator. There was no nothing. And so we said, man, this is really boring. But Yinji, being a good student, she put it in the dilution fridge. Now, I should tell you another story. That at Columbia, you would not believe that until a few years ago, we had no dilution fridge. And then Corey got rich, and he got a dilution fridge. Now he has a second one. Okay, let's not go there. You know, there's a thing called degradation. Okay, it doesn't happen in theory, but happens in experiment. Anyway, so you know, but you have to fight because everybody, my group, everybody's group wants to put a sample in the dilution fridge. So Yinji somehow got her sample in the dilution fridge, and hey presto, at about half a Kelvin, the sample turned out to be a superconductor. And then all of a sudden, Corey tells me, hey, superconducting. And so, whoa, wow, where did that come from? And of course, we found out that Phi had already seen this like a couple of weeks ago, as always is the case with Phi and G. And so you should see their work as well. Okay, anyway, so that's the story. His angle is different. That story is a little different, but okay. So now, there are many mysteries here. So one is, this is 5 degrees. This is the same sample as in 2020. We saw a well-defined insulating phase. Here, there was no insulator. So we scratched our head for a little while, and 3 minutes, okay. And we asked, we tried to figure out what could be different about this 5-degree sample versus the other 5-degree sample. And then we asked Yinji, and Yinji said, oh, I used a thin boron nitride for this sample. So we were like, Yinji, why do you use a thin boron nitride for this sample? And she couldn't give us a proper answer why she used a thin boron nitride for this sample. But that's the reality. In the old sample, the boron nitride was maybe 30, 40 nanometers thick, which is about 10 unit cells in lateral size. In this sample, the boron nitride is maybe 3 or 4 nanometers thick, which is, about a unit cell in size. Now, you can ask, is this important? In order for this to be important, we'd have to confirm this. But we are state of the art, which means we have the data on this one sample. So when we have more samples, then we'll say more about that stuff. Okay, but if you look at where superconductivity occurs in this sample, and you go back to our 2020 paper and ask where on the phase diagram superconductivity was seen, happens in the same place. The only exception is here, there's no superconductivity seen. There's no insulator seen on this new sample, but otherwise it's the same. Okay, so now, okay, I didn't even explain this plot to you. So this is displacement field, this is density, this is the resistance, and here is the region where the resistance goes to 0. So it goes to 0 at some value of displacement field and some value of density, and this is not at unity filling, different from Phi's data. It's away from unity or half filling. What I hope all of you can see now that I've told you about the Van Hove singularities, you can see what this Van Hove singularity is doing. It's doing what we expect it to do. It starts at 0 displacement field here, and then it moves away exactly as I told you earlier. And you can see that this thing happens very close to where that Van Hove singularity was in what I told you earlier. Now, here is now a zoom in on that superconducting pocket, and you see it has this funky shape. It has this fish head, arrowhead, whatever shape here. And so this is the region of 0 resistance, and right outside the region of 0 resistance out here is a region of relatively high resistance, right? And I'm going to explain this to you, but to preview what the story is going to be, this part is exactly that Fermi surface reconstruction region that I talked about earlier. Okay? And so this superconductivity occurs immediately adjacent to where that Fermi surface reconstruction happens. I'm getting in tension now because I'm getting all these signals. So here is a point here. You see it has a nice superconducting transition. And if I go just outside this, it's metallic down to low temperature. And I'm going to jump over all these things, which shows that it's a superconductor. I'll say one thing, that we can extract some coherence length from this. In this sample, it's not completely clear whether superconductivity is limited by the Pauli effect or by orbital effects when you apply a magnetic field, and that's because the G factor is large. So both of these are kind of close to each other. Okay, so in order now to study this Fermi surface reconstruction, which is what I was telling you about earlier, we can just go above Tc. So here we go to a temperature that is, or we can apply a small magnetic field, 200 millitesla. And now you see this is the region of the Fermi surface reconstruction. This is the Hall effect. And all of the things that I told you about earlier for the previous sample, they all apply equally well here. If you see what the Hall effect does, it does the same nonlinear business. All of that stuff is exactly the same. So I will not belabor that point again. They're all the same. So if you put all that together, this is the eventual phase diagram we have. This is the region where we have that Fermi surface reconstruction or antiferromagnetic state that we believe. And immediately adjacent to it is this superconducting pocket, which has this particular shape. Now, the superconducting pocket, which has this particular shape, the superconductivity disappears in different ways if you sit at different points on this pocket. If you sit at this region of the pocket, which is far away from this magnetic phase, and I measure at slightly higher temperatures, then the superconductivity decreases gradually. So Tc kind of goes continuously to 0 as I go in this direction. But as I go here, as I cross over from the superconductor to the antiferromagnet here, there's a very abrupt change as I go from the superconducting state to the metallic state. And the way you can see that is by simply raising the temperature. So as you raise the temperature, this particular boundary, you can see it kind of gradually shrinks. But I hope you can see that this particular boundary, which is where it hits the magnetic state, stays more or less constant until eventually superconductivity is completely gone. My time is up. I've expired. Okay, so we have some weak evidence that there's some hysteresis at this boundary. And let me just throw out a theory slide. No, let me not say anything about theory. You guys are theorists. So, okay, here are the observations. Magnetism and superconductivity lie near the Van Hove singularity where the density of states is high. It's somewhat unfortunate, but the density of states along the Van Hove, if I start from 0 displacement field and I go up along this direction, it turns out that the density of states actually increases along that line, right? Very unfortunate. I was hoping that it would not. But also, if you look at the susceptibility to magnetic order, that also increases as you go up along this particular direction, right? So why does one question one can ask is superconductivity is tied to this Van Hove singularity. Why does it happen there near that magnetic order or that other order? It could have happened here, right? And if the density of states was highest here and superconductivity did not occur here, then I would very proudly say it has to be some spin fluctuations or something like this. But since the density of states is also sort of increasing along this line, there may be other explanations. Okay, so I hope that was not too confusing, and I'll stop there and take your questions.
If you increase the magnetic field, are you able to see if whether that first band has a non-zero Chern number if you measure the Landau band?
So we've seen nothing, sorry, non-zero Chern number where?
For the equals 1 in steady state.
There's no Chern insulator that is close to nu equal 1 in this range of angles.
I see. So another question is, do you have any experimental evidence other than theory to show that almond-shaped pockets is actually antiferromagnetic?
So only the things that I talked about here. So we are thinking about how one could detect this antiferromagnetism in an independent experiment. But if you have ideas, let us know.
So I was just curious, in the two samples, let's say that superconduct, in your case, at 5 degrees, what's the different TCs? I mean,
So the older one was before dilution fridge days. So it was like 1.2, 1.3 Kelvin, and we could see it have zero resistance. Here the TC is quite well measured. It's little less than half a Kelvin, 450 millikelvin.
So maybe that's the effect of the HBN. Would you put any money on that?
Okay, I shouldn't speculate such things. I think we need to make more samples.
It has a large effect on the screen.
Okay, let me say this. So in our older work, we measured samples between 4 and 5 degrees. I'm convinced that if we put all of those samples in the dilution fridge, every one of them would be superconducting. And within the next year, we will redo that. And
if you could get the evolution of that pocket, the function of the angle would be very nice.
And it has to connect up to phi's data eventually, which is at sort of 3 degrees. And there it will come close to half filling. But how it does that is something we'll figure out in the next year or so.
Thank you.
Do you have a plot of TC going along this line, how it goes from 0 to climbing to 300, 400 millikelvin?
Yeah, it's not really a plot of TC, but you can sort of see at different temperatures the boundary of the superconducting pocket.
Yes, so if it is only due to a density of state effect, you should have like a sort of bound on how fast the TC can rise. If the density of states, I don't know, changes by 50%, then you can't go all the way from 0 to 300. So maybe you can bound these things by looking at how fast TC grows versus how fast the density of state grows.
I think there's lots of things that go in there, and that's sort of above my pay grade, and I'm not sure I would believe anybody who told me anything about that. But we have eminent theorists here, so.
Do you understand from theory or intuition why, as the density of states grows, these pockets of superconductivity and band renormalization only exist over a narrow patch of D?
So let me see. So this is a calculation for the density of states. This is within Andy's more recent calculations. And this peak is supposed to be the Van Hove singularity. And the point I was making was that if you look generically and you see what the density of states of the Van Hove singularity does, is it actually keeps increasing, and this is some higher order Van Hove singularity, which we never reach. And they also have plots of the spin susceptibility here. And this is done at, what is this? This is done at some value of displacement field. I don't think they have a clear picture for why it should happen stronger at some non-zero displacement field.
I guess what I'm asking is, do you understand why as you continue to raise D, if the density of states just grows, these phases don't get stronger? Is there some proximity to nu equals 1 that matters if you go back to your conclusion slide?
Yeah. So good question. So I think within this theory, I think it's true. I need to confirm. So this is just the density of state, just keeps increasing that way. I need to ask him about the susceptibilities. I believe that those also just keep increasing within this level of theory. I don't know if anybody else has a comment on this. Yeah.
Thank you very much. So I understand that the magnetism, it's also in a very localized region around this superconducting phase, right? So you don't see magnetism also following the Van Hove.
Yeah.
And therefore, you are making some comment about the possible relation or not of the superconductor, so maybe competing phases that you have in this region. So my question is also, why don't you see magnetism anywhere else? So what is also special about the magnetism in this spot there?
I guess the boring answer would simply be that, you have some Stoner criterion, and the susceptibilities increase as you go along this Van Hove line. And so at some point you sort of have magnetic order. That would be sort of the boring answer. I don't have any smarter answer than that.
Indeed, you have a Van Hove all the time. So you wouldn't see any special argument to say at this point the magnetism should be there and nowhere else. So that's why, okay, I think this is something very interesting. Thank you.
Nice talk. Do you have any evidence of phase coherence in the superconducting phase, like Fraunhofer oscillations?
Yeah, there's some Fraunhofer or maybe it's not here. Yes, there is some Fraunhofer data. No, this is just critical current. There is some Fraunhofer data. Yeah.
More of a clarificatory question. So the samples you showed in the first part of the talk, they're different. That's a different sample from the one you saw, the superconductor. Is that?
So there was one sample around 5 degrees in the old batch of samples, which was done with thicker dielectric, where we saw zero resistance at around 1.2 Kelvin. That was the lowest temperature we could reach at that time. The other samples did not show any hint of zero resistance down to that temperature. And now with this recent sample, there's exactly one sample that's been measured in a dilution fridge, which has 5 degrees twist, but also has a thinner BN. So there's now the phase space of all the old samples with thicker BN, which we should put in the dilution fridge, and also perhaps change the BN thickness and see if that affects things. And that's sort of what we're doing now.
So the sample you showed, which had an insulating phase, that was not superconducting, at least down to 1 Kelvin?
The 5 degree one, I believe, was.
It is, okay.
Yeah. But not the 4 degree or 3 degree ones at 1 Kelvin.
I think we have time for about one more question.
Have you looked at in-plane field dependence of any of this?
It does absolutely nothing.
Nothing at all.
Because, you know, the spin orbit is so strong.
Well, that's my question. Yeah, okay. Nothing. Any of these phase boundaries are just straight.
I mean, the thing is that it's tough to align the sample right. And so unless you really have a good rotator, I think Corey, they tried it in the lab fridge, but they don't have a good rotator. And
okay,
so you see something, but it's almost 100% due to some small misalignment and not due to the actual in-plane field. We've done this on the non-superconducting samples to see if you can see any effect up to high field in the mag lab, and there's nothing at all. So I would highly doubt that there's anything.
Abhay, I'm not going to argue because you didn't see any in-plane parallel field effect, but that is not explained by spin value locking because orbital magnetic field effect should happen because in the two layers there may be FFLO coupling. We are writing a paper precisely on this thing showing in a high field you should see some effect. Nothing to do with spin. It's not Pauli blockade, but orbital thing because there are two layers. So there could be an outer plane, and in fact there should be an FFLO coupling. There should be.
What's the field scale expected?
Yeah, I don't remember the numbers. These results came out this week, but if you look at my talk here from Wednesday, we give results for your sample.
I see.
How the I told Corey also.
Okay. Very good. Cool.
Thank you to Abhay.
Okay, thank you.